All right, from the front side, you saw the different types of forces that we're going to categorize each force as, so gravity, friction, normal, and tension forces. But really, when we're applying this to physics in our class, in just in understanding situations, we need to make some sense of them or kind of apply them to an object that we can make quick decisions about. So what we're going to draw are free body diagrams, or also sometimes called force diagrams. Either one means the same thing. And there are a few kind of rules to drawing those, or just kind of trends. So the first one says identify the system or the point and the point particle. Identifying the system is talking about circling. So literally circle whatever objects are being talked about and then simplify those objects or that system with a dot. And you can make it a dot or a box. Both are acceptable. Sometimes the dot is better to use and sometimes the box is better to use, but it's up to you if you have a preference. So looking down at these scenarios below, if I were talking about this, the first one, usually people do it in a dash line. It doesn't have to be. I'm just literally circling the system or the object I'm talking about, and in my force diagram, I will draw it with a dot. The next one says drawing force vectors. Arrows will show direction of a force, draw them relative sizes or magnitudes, right, to represent how big that force are, and identify or label that force type. So if I'm going to label something like FG, FG is going to just be labeled next to whatever it is. The next one says on-by notation or agent-object notation. This one is anytime we write a force, so if we have FG written there, I'm going to write it again. For each force, write what object the force is acting on and by what thing, or usually that's what it's called, an agent, that force is applied. So if it's the force of gravity, this one is always on, and then you could put in the blank on whatever, on you. And gravity to us is happening by the earth. So the earth is causing that force of gravity on you. Those are the simple kind of directions on keeping those force diagrams straight. What we have below, you have 5 different scenarios, and they have a pictorial representation, a description of the motion. You are going to draw a motion map, a force diagram, and leave this last column blank until the end. What we're going to do, since it's on a video, you're going to see a video of the motion. After you see a video of the motion, we are going to describe it, the motion. You are going to draw a motion map, and then I really want you to pause, and at some point in this, pause before I finish drawing them to actually try and draw them yourself. Because if you are really trying to check if you understand what's going on or know how to apply, you definitely want to try it on your own before seeing my answers or before seeing me do it. So definitely pause and give yourself some time to think it through before you press play on the video. All right, here is the first video. While you're watching for this air puck to come by, I want you to think about what type of motion do you see. So it will play twice. After looking at that video, the hockey puck was just moving to the right. And if you looked really closely, you would see that it was moving to the right at a constant velocity. To draw a motion map, we've done those a few times now. We would just see arrows that are the same magnitude to the right. So for this one, take a second and try to draw the force diagram on your own. And then when you're ready, hit play to see me draw the force diagram for you. So go ahead and hit pause now. Okay, to go over the force diagram, I usually like to go through the forces and say to myself, well, which ones do I have? First one I always like to look at, assuming we're on Earth, the force of gravity. So I'll label that Fg. Straight down because the center of the Earth is assumed to be straight down from us. And this one is on the puck by Earth. The next one is, let's see, do we have any normal forces, friction forces, or tension forces? No strings. And as far as friction, this is considered to be a frictionless motion. So no friction. What I do have, though, there has to be some force upward, and really what's down under here are air molecules. And those air molecules, there's a fan inside, the fan is blowing down, and those air molecules are then pushing this hockey puck up. So that one is, I'm going to call it Fn. So on puck by air. This is a really weird one because you don't normally think of air as a surface, and we talked in class about how that might be the air resistance or something. So I'm totally okay whatever you called it as long as it wasn't tension or gravity, but just realize there is a force up. Some of you might have drawn a force to the right just because it was moving to the right. But remember, forces do not show us the direction of motion. They are showing us the direction of acceleration. So within this diagram, you do not have anything to the right. It was just moving to the right to begin with. And as we remember from our front side, the law of inertia, an object in motion is going to tend to stay in motion until some force acts on it. So this object is moving to the right. It continues to move to the right. Okay, let's get ready for the next video. The next video is of this scenario here. All right, hopefully from that one we saw that the object, as much as I tried, was not moving. So there was no direction of motion. And the motion map would just show simply the object was stopped and stayed stopped for however many seconds we were talking about. Drawing a force diagram, we first want to identify our system, and then we're kind of looking for what forces act across that system boundary. First and foremost, remember we're simplifying with a dot. We can remember that our force of gravity on the book now by Earth is straight down. Then we can question, is it resting on something or is it touching something? And yes, it's resting on the table, and those electron shells must be repelling against those electron shells on that book. So we call that our normal force on the book by the table. And then you can see clearly my hand was trying to push it to the right. So my force is simply to the right. For what my force, the force of my hand is, it's not tension, it's not friction, it's not gravity. So we're going to label that Fn. And to specify that it's a different Fn than the table, we're going to call that Fn2. So Fn2, and it's on the book by my hand. And last but not least, we think of why did the book not move? The book was at rest. We had to apply a force to get it to change its motion, but there is a force acting on it that we don't necessarily see all the time. So this force being, there must have been too much friction, and the intended motion was to the right, which my force of the force applied by my hand was giving it, but the friction between the table and the book must have been to the left. It was in the direction opposite of its intended motion. So that was frictional force, and specifically a static friction, so FFS, and it was on the book by the table or by the surface, kind of whatever you would write there. So that's our next one. Now we have another video for this next scenario. So watch and try to write that description of motion for what you see. All right, for that one, we saw the book sliding to the right, but it was slowing down. Again, moving to the right. If I were to draw a motion map, we know that it's moving to the right, but getting smaller and smaller velocities as we go, which would imply that our acceleration is to the left. The force diagram for this one, I have FG down again, on, book, by, earth. Hopefully that will be your favorite one soon. The next one, we have it sitting on a table. Oops, I forgot to circle my system. So definitely earth, it's on the earth. It's on this table that's pushing up on it. So FN on, book, by, table. And then we don't see anything pushing it to the right. It's just moving to the right. But there must be a force that is causing it to change its motion, or else we would see what we saw in the first example. So down here we have what type of force. Remember, this book and this table in contact, and those atoms, those rough surfaces, they're not smooth. So while this is moving, you have that friction being applied. Since the motion is intended to the right, the friction has to be to the left. So FF, and then now K for kinetic friction, meaning it's that moving friction. So on the book, by the table, or the surface, whatever you want to call it. No other forces, no tension force, nothing else we can consider. All right, one last one. So let's look at this scenario. All right, for that one, we saw our system was our book again. And in this one, hopefully you can tell that it was moving at a constant velocity. So, and it was moving to the right. If I were to draw a motion map, we would again see that I just had constant velocity to the right the whole time. But this one's different than the first scenario because I was pushing it to the right. So it wasn't just in motion. I had to kind of consistently push on it to keep it in motion. So my force diagram, start with force of gravity on, book, by, earth. It's sitting on the table again, so FN on, book, by, table. And then obviously you see my hand crossing that system boundary, pushing on it. So FN2 on, book, by, hand. And then again, just like in our previous scenario, our previous two scenarios, we have that book being moved across the table, those rough surfaces. So there's a frictional force that's opposing that motion. So we also do have FFK again on, book, by, table. All right, now look for the video of this last scenario here. All right, what we saw from that one, our object or our system is still the book, and the object is speeding up as it moves to the right. So our motion map would look like this. With those velocity vectors getting progressively larger, and then we would have to have our acceleration arrows there like that. Again, go ahead and try that force diagram, and then check your work. This force diagram, we have, going through my list, force of gravity down, on, book, by, earth. our normal force from the table up. Again, remember this is that perpendicular one. Fn on book by table. And then for these, I have my hand is crossing that system boundary and applying a force to the right. I'm going to label this Fn2 on book by hand. And the last one, I have friction opposing that sliding motion to the right, so friction is parallel but to the left. FFK on book by table. Notice on these force diagrams, I've drawn my force magnitudes or the vector sizes relative to each other. So if we look on this one, we have my normal force is equal to my force of gravity. Above, same thing, Fn and Fg are equal to each other. For this one, FFK and Fn2 are equal to each other. Fn and Fg are still equal to each other. FFK, we have nothing to compare it to. And then for this one, Fn and Fg are equal to each other. FFS and Fn2 are equal to each other. And for the top one, the hockey puck, Fn and Fg are also equal to each other. I used 3 congruency marks just to make sure we weren't talking about the same mass of the book. From these, knowing that we have these force diagrams drawn correctly, take a second and think to yourself, well, what are some conclusions you can draw about force diagrams and the motion of an object? So before in our lab we did what can you conclude about the force and the motion of the object, but this one specifically, look at the force diagrams and the motion of the object. So go ahead and hit pause, think to yourself if you can come up with anything, and then hit play when you're ready to move on. Okay, taking a look at what we have here, notice that we have different scenarios. Of these 5 different scenarios, we have 2 of them where the object is accelerating. One time it's slowing down, one time it's speeding up. For all of the other scenarios, no acceleration, we have constant velocity, not moving, so no acceleration, and this one is also constant velocity, so no acceleration. If I'm looking at the no acceleration force diagrams, I notice a large difference from those and the accelerating force diagrams. To summarize it so simply, no acceleration, so things that have no acceleration have balanced or even or symmetrical forces in both the horizontal and vertical directions. So notice over here, these two, if you were to even say magnitudes, they cancel each other out vertically and horizontally. And then skipping down here again, cancel each other out vertically and horizontally. So then that leaves us a conclusion of the force diagrams that are balanced. The ones that are not balanced are things that are accelerating. These objects have unbalanced or uneven or unsymmetrical forces in at least one direction, and that could either be horizontal or vertical. So looking at my pink circles here, this one is unbalanced. These top and bottom cancel out, but this is left unbalanced. On the bottom diagram, the top and bottom cancel out, But this force to the right does not cancel out the force to the left because it is much larger. So if you were to add them together, this one is still left over. So the big take home here is that objects will have balanced forces if it is not accelerating, and objects that are accelerating will have unbalanced forces. I want to go back to the front side to really bring this home. So we did learn from our little ping pong ball lab, or whatever balls we were using, that the acceleration, or the direction of the acceleration, is the same direction as the force that we had in the lab, but truly this is supposed to be the same direction as the net force. The reason that we got away with just saying force for that one is because we were using balls that roll very easily on tables and allowed us to ignore friction. So therefore our net force was the air gust force. And the same with the blank force direction, so the net force direction does not determine the direction of motion. For Newton's first law, an object in motion tends to stay in motion, an object at rest tends to stay at rest unless acted on by an unbalanced force or net force. And this is when we talked at the bottom. When you add all of these forces together, the sum of the forces is the net force. So sigma F means the sum of the forces. Net force means the sum of the forces. And this is also just kind of giving you an example. This is talking about a force diagram that when you add all of them up, the sum is non-zero. So if something has a net force, usually you're talking about the fact that the sum is non-zero. Or if you talk about the net force, you might say the net force is zero, and then therefore it's balanced. But just for some verbiage, sum is non-zero, so you see uneven forces on a force diagram. So to conclude this entire thing, the idea on the bottom kind of says, just because something is moving to the right does not mean that there is a force being applied to the right. That goes back to that first sample with the hockey puck. You might want to say there's a force causing it to move to the right, but it's just the fact that it was moving to the right at some point and there's no opposing force. We generally really miss this because of the fact that we have friction in our world and we think of everything without seeing the friction. We see the other forces that are acting there. So anytime you know something about the motion, you can infer something about the forces acting on that object. And if we know about the forces acting on that object, we can deduce what the motion would be like. So using these force diagrams is going to help us a great deal in looking at the motion and acceleration or constant velocity of these objects. All right, make sure you finish up that practice for homework.